Hello, today I want to prove Fermat's Christmas theorem, which tells us that if we are given any prime number p which is of the form of 4k plus 1, then we can always find a and b positive integers such that a squared plus b squared will be equal to p. To prove this, we need to use the lemma that if we are given any number, any positive integer u, then we can always find x and y in this range from negative square root p to square root p such that x times u will be equal y mod p. To prove this lemma, let's discuss the equation xu minus y, and in this case x must be from 0 to square root p, and similarly for y. And how many different choices do we have for x? We have exactly square root p plus 1 different choices, and for y we have also square root p plus 1 different choices. So in total this equation may have square root p plus 1 different residues mod p, but it is impossible that all of them may be different, because in total we have at most p different residues modulo p. So this means that we can find two numbers x1 and y1, two pairs x1 y1 and x2 y2. This equation has the same remainder, so if we discuss their difference, it must be divisible by p. So xy minus xy times u minus y1 must be equal x2 times u minus y2 mod p. Now let's discuss the case then x1 minus x2 times u minus y1 minus y2. This number must be equal 0 mod p. So we can conclude that this number must be in the range of near negative square root p to this number is here, and this is less or equal to square root p. Similarly, we can conclude for x1 minus x2, and then we have shown that in this range from negative square root p to positive square root p, we can always find two integers. Their x times u will be equal y mod p. Now let's get back to our initial problem, and now we need to use the fact that negative 1 is a quadratic residue for all primes which are 4k plus 1 type. And how can we conclude this? Because of Legendre's symbol, negative square root p pi must be negative 1 to the p minus 1 half. So this must be negative 1 to the 2k. So this is 1. So we can conclude that there will exist some negative integer u, such that u square must be equal negative 1 mod p. Now let's discuss this u and x and y. If we multiply both sides by y, nothing will be changed. So x u square must be equal. Now let's discuss. If we take this equation into square, like we get xu square must be equal y square mod p. But if we take instead of this u, this one, so we get that negative x square equals y square mod p. So we get that x square plus y square equals 0 mod p. But how many different choices do we have for this sum? We have almost 1 different choices, because x square is less or equal to p, but this is impossible that this number can't be equal to p, because square root p is not integer. This is not integer for any prime. So x square plus y square must be less than 2 times p. But if you know that this number is divisible by p, this means that x squared plus y squared equals exactly p, because the x is only one number which is multiple of p and less than 2 times p, and so we have concluded that we managed to found two integers x and y such that x squared plus y squared equals p. So we have proved Fermat's Christmas theorem. If you want to discuss another theorems, please write in the comments.